Okay. Ever try using a spoon as a mirror? We've all been there. Turns out there's a whole lot of science behind why reflections look the way they do.
Mm,
You shared some fascinating notes on the physics of light,
right.
and I'm ready to get schooled. Beyond the basics, that is.
Well, what's fascinating is how we basically take light for granted.
Uh-huh.
This is how we experience the world.
That's true.
But we don't often stop to think about the mechanisms behind it.
Right. It's like, yeah, light exists, but how does it work?
Yeah.
Like, we know it travels in straight lines. That's why you can't see around corners.
Exactly. And the source material had that great example with the candle and the bent pipe.
Yeah.
No matter how much you try to peek, the light can't bend to your viewpoint.
Oh, so true. But then shiny surfaces come in and change everything.
Right.
That's where it gets kind of mind-bending.
That's reflection at work.
Okay.
So imagine, light bouncing off a surface,
Okay.
like a perfectly thrown ball rebounding off a wall.
Okay, that makes sense. But water reflects light, too.
It does.
And those reflections always mess with me.
Yeah.
Like, remember that story from the Panchatantra, the one with the lion and the rabbit?
Oh, absolutely.
Talk about reflections gone wrong.
Classic tale of trickery
Yeah.
and perspective.
Yeah.
The lion mistakes the rabbit's reflection for another rabbit.
Right.
Because the water acts like a mirror
Right.
reflecting light to create that illusion.
Poor lion. But it shows how, convincing reflections can be, little
Definitely.
optical illusions happening all the time.
Yeah.
Speaking of which, how do reflections work with angles? It feels like there's some secret geometry going on.
Yeah, you're right. The geometry of it is crucial.
Yeah.
Your notes mentioned an experiment
Okay.
where you shine a light with slits in it,
Mhm.
creating beams of light
Okay.
onto a mirror.
Oh, right.
Yeah.
Like, you could see exactly where each beam hit the mirror and bounced off.
Precisely.
Ah.
And by changing the angle of the light hitting the mirror, what we call the angle of incidence,
Mm-hmm.
we change the angle at which the light reflects off.
So it's not random at all.
Not random at all.
Okay.
Yeah.
But even though the angle changes, the reflected light still travels in a straight line, right?
Absolutely.
Okay.
Reflection changes the light's direction,
Okay.
but it doesn't change its fundamental nature of moving in a straight path.
Right.
And this consistent behavior
Okay.
is what makes things like mirrors possible,
Right.
especially the flat ones we use every day.
Yeah.
Plane mirrors?
Right. But even something as simple as a plane mirror can get weird fast.
They do.
Like, why does a mirror flip left and right, but not up and down?
Right.
It's like it's deliberately messing with our sense of direction.
That's the intriguing phenomenon of lateral inversion.
Okay.
Let me paint you a picture.
Okay.
Imagine standing in front of a mirror pointing to your right.
Okay.
Your reflection points to their right, which, from your perspective, appears on your left.
Wait, so it's not actually flipping left and right? It's more about our perception
It is.
from our viewpoint.
It is. Yeah.
That's kind of trippy when you think about it.
It is, and it has real-world implications.
Okay.
That's why ambulance writing is reversed, so
Wow.
drivers see it correctly in their rearview mirrors.
Whoa, that is wild. It makes you wonder how many other everyday things are designed around these, hidden tricks of light.
More than you'd imagine.
Right.
But plane mirrors are just the tip of the iceberg.
Okay.
Let's dive into the world of curved mirrors. Concave and convex.
Okay, so concave is curved inward, like the inside of a spoon.
Yes.
And convex is outward, like the back of a spoon.
You got it. The source material used a clever example.
Okay.
Imagine carefully slicing a section off a rubber ball.
Okay.
The inside curve you create would be concave,
Uh-huh.
and the outside would be convex.
Oh, that's a great visual.
Yeah.
And I bet the way these curved surfaces reflect light is totally different.
It is.
Like those concave mirrors you see in movies that can focus sunlight and burn things.
You're spot on. Your notes mentioned an experiment doing exactly that.
Really?
Focusing sunlight with a concave mirror onto a piece of paper to make it smolder.
Okay. That's both cool and slightly terrifying.
Yeah.
So how does that even work?
It all comes down to how concave mirrors can create what we call real images.
Oh,
These aren't like the virtual images we see in a flat mirror.
okay.
Real images can actually be projected onto a surface,
Right.
which is how you can focus the sun's energy so intensely.
That makes so much sense now.
Yeah.
And I bet that's why concave mirrors are used in so many things, not just scary science experiments.
Precisely.
Right.
They're in flashlights to direct a concentrated beam,
Mm-hmm.
in car headlights to project light further,
Wow.
and even those head mirrors doctors use to focus light for exams.
Wow. Concave mirrors are way more common than I realized.
Yeah.
So if concave mirrors concentrate light,
Yes.
what about convex mirrors?
They do the opposite.
Okay.
that spread light out.
Okay.
This means they always produce virtual images,
No.
just like plane mirrors,
Uh-huh.
but the images are smaller than the object.
Hold on. If a convex mirror makes things look smaller,
Yeah,
why would we want that? Wouldn't a bigger view be more helpful?
that's a great question. Think about car side mirrors.
Okay.
They use convex mirrors to give you that wide-angle view,
Oh,
so you can see more of the road,
I see.
even if it means the cars behind you look a bit smaller.
Ah, that makes sense. It's a trade-off for a wider field of view. So we've talked about reflecting light.
Yeah.
But what about bending it? That's where lenses come in, right?
You got it.
Okay.
Lenses take advantage of a phenomenon called refraction,
Okay.
which is just a fancy way of saying they bend light as it passes through them.
Right.
And guess what?
Uh,
They come in concave and convex shapes, too.
Wait, so a convex lens is thicker in the middle,
Yes.
like a magnifying glass,
Exactly.
and a concave lens is thinner in the middle. Yes.
I remember comparing them in science class.
Yeah.
It's so weird.
Yeah.
And that difference in thickness or curvature is what gives them their unique light-bending properties.
It sure does.
Okay, I'm ready to get into the details.
Right.
But first, maybe we should grab a snack. All this talk about lenses has got me craving some nachos shaped like
Well,
lenses.
okay. Sounds good to me.
All right, lenses and nachos back to bending light.
Yeah.
So convex lenses, they're thicker in the middle,
Right.
and if I remember correctly, they can magnify things.
Yeah.
Is that because of how they bend the light?
Absolutely. Just like with those concave mirrors,
Okay.
the way that a convex lens bends light allows it to create real images,
Right.
which means those images can be projected.
Oh, right.
Yeah.
And a projected image is basically what we see when we use a magnifying glass, which is just a convex lens.
You got it. In fact, your notes even mention an experiment almost identical to the concave mirror one.
Okay. Where you can use a magnifying glass to focus sunlight, and you guessed it, burn paper.
No way. So both concave mirrors and convex lenses can focus light intensely enough to burn things?
Mm-hmm.
That's kind of scary.
It is pretty cool.
But if they both focus light,
Yeah.
what makes them different?
That's a great question. It comes down to how they each interact with light.
Okay.
Concave mirrors reflect light to a focal point,
Okay.
while convex lenses refract or bend light as it passes through to reach that same focal point.
Okay.
Two different ways to achieve a similar outcome.
Mind blown. It's like they're both playing with light, just with different rule books.
Exactly.
So convex lenses are basically the MVPs of magnification?
are.
Right.
Yeah.
But what about those concave lenses, the thinner in the middle ones?
Yeah.
What's their claim to fame?
Concave lenses are all about spreading light out,
Okay.
which makes images appear smaller.
So kind of like how convex mirrors gave us that wider field of view?
Exactly. And much like those mirrors, because concave lenses always produce virtual images,
Right.
you'll find them used in things like some eyeglasses for people who need help seeing things up close
Mm-hmm.
and even in peepholes
Real.
to give a wider view of who's outside.
It's amazing how these subtle curves can completely change how we see things.
It is.
You know, we've been talking about lenses and mirrors,
Yeah,
but it all goes back to the nature of light itself.
it does.
We kind of glossed over it, but we've always been taught that sunlight is white light, right? Is that the whole story?
Not even close.
Oh, really?
There's a hidden world of color
What?
within that seemingly simple white light.
Okay.
Remember that experiment you mentioned with the prism and the rainbow?
Oh, yeah. Shining a beam of light through a prism and seeing it split into all those colors. That's one of those science demos that always felt like pure magic.
Yeah.
But now I'm dying to know how it actually works.
It's not magic,
Okay.
but it is a brilliant example of how light interacts with different materials.
Okay. Yeah.
Each color of light travels at a slightly different speed.
No way.
And when light passes through a prism,
Yeah.
those different speeds cause the colors to bend at slightly different angles.
Okay.
It's a process called dispersion.
Mm-hmm.
That's what separates the white light into its individual colors, creating that beautiful spectrum we call a rainbow.
Wait, so it's like the prism is sorting the colors of sunlight based on how they bend?
It is.
That's incredible. It
Yeah.
makes those little crystal rainbows people hang in their windows even cooler now.
Right.
And speaking of rainbows,
Yeah.
this phenomenon of light dispersion is exactly how rainbows form in the sky.
It is.
Right?
Mhm. But how does that even work? It's water droplets that make rainbows, right?
Yeah.
They're not exactly prisms hanging out up there.
You're right. Water droplets aren't exactly prisms,
Yeah.
but they can act like them.
Okay.
When sunlight enters a raindrop, it gets refracted or bent, just like it does in a prism.
Okay.
That light then bounces off the back of the raindrop.
And gets refracted again as it exits.
Really?
This double refraction is what separates the white light into its different colors,
Oh.
creating that familiar arc of a rainbow.
Whoa, so every time we see a rainbow, we're actually seeing all the colors that make up sunlight being put on display.
We are.
That's mind-blowing.
It is pretty amazing.
But it makes me wonder, if sunlight is a mix of all these colors, why does it look white to us?
Yeah.
Shouldn't we be seeing all those colors all the time?
You're asking all the right questions.
Yeah, my.
And to answer that, we need to talk about how our eyes perceive light.
Okay.
You see, the human eye has special light-sensitive cells called cones that are responsible for color vision.
Okay.
We have 3 types of cones,
Okay.
red, green, and blue.
Right.
And each type is most sensitive to a particular range of wavelengths within the light spectrum.
Okay, so red cones are for red light,
Yes,
green cones for green light, and blue cones for blue light.
exactly.
But how do those 3 colors make all the other colors we see?
That's where things get really interesting.
So we've got these red, green, and blue cones in our eyes, and they're mixing signals, like
Yeah.
some kind of color cocktail party in our brains.
That's one way to think about it.
But how does that explain why we see sunlight as white?
It's the ultimate color combo.
Okay.
When all the colors of light, the whole rainbow, hit our eyes at the same time,
Right.
it stimulates all 3 types of cones
Okay.
roughly equally,
Okay.
and our brain, taking in that full spectrum symphony of color,
Right.
interprets that balanced signal as white light.
So white light isn't its own thing.
Right.
It's the full band being played at once.
Exactly.
That's incredible.
It is.
But hold on.
Yeah.
If white light is just all the colors mixed together,
Yeah.
shouldn't we be able to unmix them?
Exactly. And you actually mentioned one way to do that earlier.
Did I?
The Newton's disk experiment from your notes.
Oh, right. I totally forgot about that.
Yeah.
It's a spinning disc.
It is.
Yeah. But I'm drawing a blank on how that separates out the colors of white light.
It's a clever demonstration of how our perception of color works.
Okay.
Imagine a disk divided into sections, each painted a different color of the rainbow.
Right.
When the disk spins rapidly,
Yeah.
those colors blur together.
Right.
And if you spin it fast enough,
Yeah.
the disk appears white.
Wait, so it's like our eyes can't keep up with the spinning colors,
Yeah,
so they
yeah.
just blend together in our brain
Right.
and we see white.
Exactly.
That's both fascinating and makes me feel like my brain needs a nap.
Right.
Too much color.
It highlights how our perception of the world
Yeah,
is limited by how our brains process information.
totally.
But there's one last thing I want to touch on.
Okay.
Something that ties back to our very first topic.
Okay, what's that?
If light travels in straight lines,
Right.
how do we see objects that aren't directly in line with our eyes?
Ooh, you're bringing it full circle. Okay.
Yeah.
So if light can't bend around corners, but we can still see things to the side of us,
Yes.
something else must be going on.
Something else is going on.
Right.
Yeah.
I'm stumped.
It's all thanks to another fascinating property of light called scattering.
Scattering. Okay.
When light hits tiny particles in the air like dust, water vapor, even molecules themselves
Okay.
get scattered in different directions.
So it's like the light takes a detour.
In a way,
Mm-hmm.
some of those scattered light rays end up reaching our eyes.
Okay.
Even if the original light source wasn't pointed directly at us,
Okay.
that's how we see things that are off to the side, or even why the sky is blue.
Wow. Light scattering is like this whole hidden layer of how we see the world.
It is.
This deep dive has been incredible.
It's been fun.
I feel like I've gone from like basic knowledge to having my mind totally blown wide open about
Yeah.
something I thought I understood.
It's always amazing how much there is to learn
It is.
about something that seems so simple on the surface.
So true. Well, thanks to everyone for joining us for this illuminating deep dive.
Yes, thank you.
Go forth and appreciate the wonders of light and maybe carry a prism in your pocket,
Good idea.
just in case you need to create a little rainbow magic.
Always good to have a prism handy.